Earlier this month, I made a trip from Ireland to Dubai, and as the plane climbed to cruising altitude, we were treated to the most amazing sunset from 12 kilometers in the sky. I had this moment of awe and gratitude that we live in a time where experiences like this are possible, and the feeling just got stronger when I arrived in Dubai and saw the Burj Khalifa. The building defies belief. I lived in Malaysia for 3 years and used to love watching the Petronas Twin Towers glimmering in the distance as I drove through the hills of Bangsar. Those towers held the title of the tallest building until 2004, but the Burj Khalifa is almost twice the height. I found myself looking up the tower, and where I expected them to stop, they just kept going, soaring further than I thought possible. And it really got me thinking about how its engineers managed to overcome the challenges that faced them. The battle to build higher captured the world's attention in 1929 as the Chrysler Building raised its secret spire like a proverbial middle finger to the Bank of Manhattan Trust Building. After months of intense competition to become the world's tallest building, it cemented Chrysler as a powerhouse in the American automotive industry, becoming a symbol of the company's power and technological prowess. The soaring skyscrapers of Manhattan were not only a symbol of the power of the companies that built them, but were seen as an expression of America's optimism and wealth. The explosion in growth in America was largely fueled by the invention of the elevator and the availability of cheap structural steel. Frank Lloyd Wright even proposed the Illinois, a 1.7 kilometer tall building, in 1956, and while this building was theoretically possible, it was completely unpractical. Elevator technology had not advanced far enough, and building sway would have been a huge issue for comfort. Tall, slender structures like this are susceptible to wind-induced vibrations. Anyone that has seen lampposts shaking in the wind will have seen this in action. So what's happening here? Let's place a cylinder in a wind tunnel and examine what happens as we increase the air velocity. In a steady flow of air, you would assume that the net force on a cylinder would be in the same direction, like this, and you'd be right. At lower speeds this is the case. Here the light bulb would just bend in that direction, and while the wind speed and direction may fluctuate, you wouldn't see these consistent back and forth vibrations. As we increase the speed, the air begins to separate from the surface of the cylinder, creating two symmetrical eddies behind the cylinder. Eddies are regions of slow-moving, swirling fluid. You'll see these a lot in rivers where branches or bridge pillars block the flow. Here is one in my hometown of Galway. Kayakers use these eddies when they need to rest from the fast-moving mainstream. If we keep increasing the fluid velocity, these eddies will grow, and the force on the cylinder will also grow. But as long as these eddies are symmetrical, the force will remain in the direction of the fluid flow. But there is a critical moment where the system loses its stability. The energy gradient from the mainstream and the slow-moving eddies becomes too high, and eddies begin to oscillate. At this point, a phenomenon called vortex shedding occurs, and the resultant force is no longer directly downstream. It teeters between the alternating low-pressure zones as the vortices are shed on either side of the cylinder. This can become a massive issue if the frequency of the shedding matches the resonant frequency of the structure. That means that the direction of sway and the direction of the force become synchronized, and the amplitude of the swaying is allowed to grow as energy is being stored between each cycle. Every building dissipates some of that oscillation energy through natural dampening, through its materials and through friction at the joints, but this is not always enough. In these cases, it is essential that the engineers add mechanical dampers. These are usually hidden away in the guts of the building, but the world's former tallest building, the Type A 101, decided to open their 730 metric ton tuned mass dampener to the public. On August 8, 2015, a Category 5 typhoon slammed into Taiwan and set the Type A 101's mass dampener into motion, and it was all recorded on a web camera. So what's happening here? How does this help stabilize the building? When the tower is displaced, the mass dampener does not move with it immediately. It is left behind and then begins to sway independently of the building. Now this is where the tuned part comes in. The engineers will have tuned the damper to the same frequency as the building, so when the building sways to the right, the damper sways to the left, and vice versa. This creates an opposing force to the sway, which is transferred to the building through these piston dampers, and thus the kinetic energy is dissipated, and the magnitude of the resonant motion is reduced. Now, what amazes me is that the Burj Khalifa has no mass damper. It simply relies on clever aerodynamics, from stopping those vortices from ever getting organized to cause harmonic motion. The reason light poles sway so easily is that they have a consistent cross-section, allowing those vortices to slough off uniformly along the pole's height, so the same force is being applied at the same time along the entire length. One way engineers combat this is by placing these helical spirals along the length of cylindrical structures. You occasionally see these with chimney stacks, but also in offshore platforms, as vortex shedding can also happen in liquids. The helical fins disrupts the fluid flow along the length of the hull, preventing the vortices from forming coherently. The Burj Khalifa works in a similar manner, albeit in a much more elegant fashion. The building's footprint was inspired by the desert Himena flower, and while this is a beautiful design, it provides an optimal amount of window space, while also allowing the steel reinforced concrete frame to take this shape. This central core provides excellent torsional resistance, while these Y-shaped buttresses provides fantastic lateral bending resistance, similar to how an I-beam works. I'll explain that more in a future video. As the tower grows, the building steps back consecutively, like this. This spiraling pattern works exactly like the helical fin on the platform earlier. It prevents the vortices from sloughing off the building coherently along its length, and so stop them from exciting the building's resonant frequency. This is the genius of the building and why it doesn't need a mass damper. The architects put meticulous care into the building's aerodynamic design, using modern computational analysis and wind tunnel tests to ensure the structural integrity of the building. It is clear that with the continuous improvement of technology, building these super tall buildings is becoming less difficult, and we are going to continue seeing the title of the tallest building in the world swap hands in the coming years, especially as the pressure to build higher grows. In 2007, the total urban population of the world surpassed the 50% mark. 20 years ago, that figure was just 33%, and that statistic is expected to approach 80% by 2050. Creating a functional city with adequate water and energy supply and everything else that comes with a densely packed population will become an enormous challenge in the coming years. It is likely that these super tall buildings will become less of a decadent symbol of power and wealth and become a necessary and fundamental part of the modern city. Thanks for watching. I really enjoyed making this video, and I hope you enjoyed watching it. I have heard back from loads of you on how much you're learning from the Great Courses Plus. And thanks to your continued support, they have decided to sponsor another video. So thank you to all my subscribers, Patreon supporters, and the Great Courses Plus for helping real engineering exist. If you enjoy my videos, you will definitely like the Great Courses Plus. They have over 7,000 different lectures from world-renowned educators. They have a huge range of topics. If you'd like to learn more about structural engineering, they even have a course for that. Or you can learn about photography, chess, and cooking. These courses give you in-depth knowledge on a variety of subjects, while allowing you to learn at your own pace without tests or exams. You can get a free 1-month trial by going to thegreatcoursesplus.com/real-engineering. If you'd like to see more content or support real engineering, the links for my Patreon, Instagram, Facebook, and Twitter accounts are below.